Hello, good morning. This is Zhang. I'm working at Pacific Northwest National Lab. I have been here for 10 years and work for the E3SM project since the beginning. So today I'm going to present our recent work on the effective radiative forcing analysis for V1 and V2. Basically, this is it includes two parts. The first part on the V1 analysis. You see a lot of names here. So those are co-authors on a manuscript recently submitted to ACP and currently in revision. And the second part is on the V2 analysis. And I used a lot of simulation performed by Chris, Xue, and Ryan. Thanks a lot for their help. And many others in the project also have a lot of useful discussions, and I appreciate them as well. So the motivation, if you look at Chris V1 modeling paper, one of the major conclusions is that the effective aerosol forcing in the E3SM V1 model is pretty large, and compared to the other CMIM6 model, which I will show later, it is also on the higher side. And so we need comprehensive analysis on a lot of the aerosol and cloud properties, and we wanted to focus on the historical changes, looking at the relationship between those aerosol and cloud radiation fields, and we try to decompose the forcing into different components, and we want to evaluate the parametric radiation sensitivities. We also wanted to answer the question whether V2 is better than V1 in terms of aerosol forcing simulation. And we also want to investigate what's the climate response to the anthropogenic aerosol effect in the coupled model. So I want to show the key points first, so that if that time goes out, you still can have the key points here. So basically, compared to V1, the TOA effective aerosol forcing is significantly reduced in both the shortwave and longwave components in V2. The net change is relatively small. It's about 0.31 per square meter. Both the first and second indirect aerosol effect magnitude are reduced significantly. However, the shortwave and longwave surface effective aerosol forcing changes are relatively small, and the reduced indirect aerosol forcing at surface is compensated by stronger direct effective aerosol forcing, and this is mainly caused by increased anthropogenic aerosol burden and AOD. Aerosol effects on the shortwave and longwave TOA radiative flux are magnified in the coupled runs. I will show some results later. And I will also show some sensitivity simulations and demonstrate that the tuning, cloud aerosol parametrization bug fixes, and numerical coupling errors all have significant impact on the aerosol lifetime, AOD, and the aerosol forcing simulated in E3SM. The last but not least, the effective aerosol forcing estimate from the nice simulation, we found that they are pretty similar to and consistent with the forcing estimate using the free running AMIP or RMIP simulations, which indicate that in future model development, we can make use of natural simulations as much as possible. And we believe that it can save us a lot of time. So I will use a lot of long simulation from the DEC simulation for V1 and V2. For the V1 simulation, the EAM V1 model version is used with the MEM4 aerosol module. The long simulation I use is from the AMIP simulation starting from 1870 to year 2014, and we have two simulations, one with the pre-industrial aerosol emissions and the other with the transient aerosol emissions. So by taking the difference between the two, I can derive the effective aerosol forcing from those long simulations. At the same time, I also performed a lot of night simulation because for the long simulation does not include all the necessary information I want to analyze. So I performed a lot of maybe 15 months long simulations with 3 months spin up and last 12 years for analysis. The horizontal wind and nudge towards reanalysis for year 2010. Only wind and nudged, and the relaxation time scale is 6 hours. And for the night simulation, I also have a per-industry run, and the other run with aerosol emissions, I selected time slices. For example, I can have a present day emission data as input, and also I can choose, say, year 1970 to look at the aerosol peak in the European, West European countries. So for wave 2, the simulation strategy changed a little bit. So if you look at the simulation setup I'm using now, so we have the RF MIP simulations with fixed SST prescribed from the coupled simulations with transient aerosol emissions. And we also have a coupled simulation also with the transient emissions. And this is called history. I take the name history aerosol. And we also have the PI control for both of them. For the RF simulation, we have 50 years with fixed SST and 1850 forcings. And for the combo simulation, we have 500 years. And also with the pre-industrial forcings. Because you see that the historical simulations with the aerosol, transient aerosol forcing has a different simulation length compared to PI control. So I have to take the mean time average of PI control and then take the difference between the historical aerosol simulation and the time mean fields from PM control to get the aerosol forcing. So the methodology is slightly different, but overall the impact, the overall trend of the historical aerosol forcing, as I show later, are quite consistent. I also have a nice simulation similarly set up for as for V1. So we can directly compile the V1 and V2 simulation in the same configuration. First of all, I would like to show the effective aerosol forcing simulated in the E3SM V1 model. As you see here, I'm showing the historical changes of the simulated effective aerosol forcing at TOA for the net, long wave component, and short wave component. So as you see here, on the right, I'm showing the Siemens 6 RF MIP model estimate from Smith et al. The cross indicates the multi-model mean, and the seam bars here indicates the minimum and maximum ranges in those model estimates, and the thick bar indicates the standard deviation. And you can see that for the net forcing, actually for our model is out of the RF MIP model estimate bound. But for component level, we are still within the range. But overall, we have a quite strong aerosol forcing in the V1 simulation. And here you also see some dots here. Those are simulations using the estimates using the nudge simulations. As you can see, for individual years, close to pre-industrial, early or the 1915 and the 1970 period, for all those time slices, the nice simulation can give a pretty accurate estimate of the effective aerosol forcing. So we'll make use of the nice simulation for most of analysis later on. So here I'm showing the effective aerosol forcing estimate by the night simulation at TOA. So I see here, I take the difference between the PD and the simulation with PD aerosol emissions and PE aerosol emissions. And here on the top, I'm showing the V1 result, and the bottom is the V2. As you can see from both the global annual mean numbers and the colors, you will find that the TOA effective aerosol forcing is significantly reduced in both short wave and long wave component. And here I'm showing the V1 AMIB free running simulation and V2 RF simulation. Again, from the historical changes, you also see that the V2 simulation have a much weaker effective aerosol forcing at TOA for individual components, short wave and long wave. Both of them are weaker. Now I'm showing the indirect aerosol effective aerosol forcing at TOA. So this is decomposed forcing based on Steve Gann's method in his year 2013 paper. If you compare the overall forcing here and here, you will see that the overall pattern are very similar, and the global mean numbers are also pretty close. And this indicates that the changes in the effective aerosol forcing are mainly caused by the reduced indirect aerosol effect in the V2 model. And I wanted to mention that there are two important model changes that affect the effective aerosol forcing in V2. One is the tuning. There are a lot of tuning parameters changed, and those tuning changes can have a significant impact on the forcing. Also, we implement minimum cloud droplet number concentration in the model simulation, and this also reduces the effective aerosol forcing. I just mentioned that at TOA, the effective radial forcing are significantly reduced. In contrast, if we look at the surface forcing, we see that the forcing changes are quite small compared to V1 and V2 simulation. So overall, the short wave component at surface only changed about 0.2 watt per square meter. And for the long wave, the global mean values almost didn't change, but the pattern changed a little bit. And this indicates that we have very different forcing changes at the TOA and at surface. And this suggests that the atmosphere heating basically the aerosol forcing and in the atmosphere column will be very different compared with V1. Again, if we compare V1 and V2, using the AMIB simulation and the RF free running simulation, we again can see that the surface forcing for the short wave component and for the long wave component, those changes are pretty small compared to the forcing changes at TOA. Now I'm trying to show you some causal relationship between droplet number concentration and effective radius and liquid water pass. Basically, the first term here indicates the magnitude of the first indirect effect. So the RE indicates the effective radius of a cloud droplet. The second term, the liquid water is the liquid water pass response to the perturbation in cloud droplet number concentration. And the top row is the V1 simulation and bottom row is the V2 simulation. As you can see, for the x-axis indicates the relative changes in cloud droplet number concentration, and the y-axis indicates the relative changes in the effective radius and liquid water pass. As you can see here, for V1 for year 2010, the present day estimate, our estimate for V1 is about 0.3 for the relative changes in droplet. But you can see for V2, this change is significantly reduced from here to about 0.2. Also, if you look at the relative changes in effective radius, the magnitude also changed from about 0.09 to about 0.08. Similarly, we see consistent changes in liquid path. So basically, both of the two indirect effects, first and second, the effect radiative forcing magnitude are reduced significantly. Now I'm going to show one of the major changes we implemented in the model. The original idea was based on previous studies on looking at the impact of lower bound of CDNC on the aerosol forcing. And the other model indeed show that this works. And we analyzed the droplet number concentration in our model using the high resolution, temporal resolution data from V1 simulation. As you can see that based on the 1 year simulation, we can see the droplet number concentration smaller than 10 per cc. This very clean conditions happen frequently in the model. As you can see, this red curve here, solid curve, and the yeah, these are the frequency of those extremely low CDNC conditions. So it happens frequently in our model, which indicates that maybe in some locations, the simulated droplet concentration is too small, and under those conditions, the impact, the aerosol perturbation will have a big impact on the cloud formation. And after we adding a lower bound of CDNC, we see consistent reduction in the aerosol forcing magnitude. In V2, we use applied CDNC minimum number of 10 per cc. As you can see here, both of the short wave component and long wave component forcing are reduced, and even for the net forcing is also reduced. So based on this V1 simulation, we can see it's reduced about 0.3 to 0.4 watt per square meter. And this is very consistent with simulation with V2. So basically, if we remove this lower bound in V2, the aerosol forcing is about minus 1.464 watt per square meter, which is about 0.3 watts per square meter stronger than in the standard V2. On the other hand, if the CDNC minimum lower bound is set to too large, we will see strong perturbation in liquid water paths in some regions in the model simulation, which is not optimal. Yeah, now I'm going to show you some surface forcing result, because we find that this indicates that the model have significant changes and it might be a problem. So here I'm showing the direct aerosol effect at surface. This is a decomposed forcing based on the Steve-Gans method. As you can see here, the top row, again, V1 simulation, bottom row, V2 simulation. For the direct forcing, we see clearly in V2, the direct forcing at the surface increased significantly, about 0.5 watt per square meter. So this is quite significant, and this will have a big impact on the surface temperature. Surface flux received, say, for example, over the ocean, if you compare those V1, V2 results, so the aerosol forcing over here is much stronger than over here. And this might have some impact on the ocean surface temperature and ocean circulation. And why that? So we analyzed the simulation from V2 and V1. And if we look at the historical changes, and we see clearly V2 have a much larger anthropogenic AOD compared to V1 simulation. So, and the RF simulation and couple simulation give quite consistent result. Basically, this confirms that the surface direct aerosol forcing increase is mainly caused by the AOD increase in the model. And the results are consistent with some analysis done by Mingxuan and Hailong. They look at the period from year 2000 to year 2014. And they also found that the anthropogenic aerosol AOD increased quite significantly. And recent scientific simulations show that a couple of tuning parameters play an important role on the AOD and aerosol lifetime. So why is AOD is much larger than V2? So if you compare V2 and V1, so the AOD increase about 0.04. And lifetime, if you look at the black carbon, it increased about 1.5 days, which is quite significant. And by looking at the aerosol barrier analysis, we find that the wire removal terms for convective clouds change significantly. So we performed one simulation by revert the tuning parameter for convection permutations, and this column shows the updated result. As we can see that after reverting those tuning parameters, the AOD is greatly reduced, and also the aerosol lifetime is reduced. And in those tuning parameter set, there are 4 parameters. As you can see, the DP1, C0, this layer index for the convection initiation, and alpha. So basically, the largest impact are caused by mainly the 2 parameters, DP1 and C0, at least from my scientific simulations. And interestingly, a recent model development paper on EchoHum, which is a European model, also reported light sensitivity of OD simulation to the convective parameterization tuning. And I would like to show some other results. Some other factors can also change the aerosol lifetime. So there are 2 important bugs recently identified and fixed in the development branch, but these bugs are still in E3SM master. The first one is the MG2 bug fixes. This is reported by NCAR, and Andrew Gantman showed some results at the ANWG workshop. And the second bug is about the aqueous chemistry bug. This is reviewed during the NDD P3 development. And both of the bugs, as you can see here, have an important impact on the aerosol lifetime. So the MG2 fix, which is a fix related to the heterogeneous ice nucleation, increase the aerosol lifetime because more ice will be in the simulation and the liquid water content decreases. And for the aqueous chemistry bug fix, it decreased the aerosol lifetime. And recently, I performed some scientific simulation together with John Wolf at Los Alamos, because there are some tuning simulation needed for the couples simulation. One of the changes made to the simulation is that the physical time step changed from 30 minutes to 15 minutes. And back out of curiosity, I looked at the aerosol budget in those simulations, and interestingly found that the lifetime decreases for all type of aerosols except for dust. And these changes are very similar to those changes seen in the V1 simulations. And as you can see, the magnitude is quite significant. This indicates that if we run the model at higher resolution, we will see some changes in the aerosol life cycles. And this is something we need to deal with in the near future. So just some final words about the ongoing effort. So we are further investigating why the effective radius is so sensitive to the changes in the aerosol number concentration in E3SM or MG2. And we wanted to fix and evaluate those important bugs as soon as possible, and also fix it in the master. Some further analysis of the single forcing couple simulation are planned. And we are also going to integrate various aerosol forcing diagnostic tools for future aerosol future model development. That's it. Thank you.